folks, welcome to example 5. All right, now that we've looked at inequalities and graphing nonlinear inequalities, let's graph a system of nonlinear inequalities. So we're just ultimately going to graph more than one. So a system of nonlinear inequalities is a system of two or more inequalities in two or more variables containing at least one inequality that is not linear. Right? So if I had something like x plus 3y is greater than 10, that's a linear inequality. But if I pair that with x squared plus y is less than 3, well, the x squared makes it a nonlinear inequality. So this would be a system of nonlinear inequalities. And the idea is to graph both of these and see where the overlap is. And we're going to call that a feasible region. And that is going to be the answer. So the solution to a nonlinear system of inequalities is the region of the graph where the shaded regions of the graph of each inequality overlap, or you could say where they intersect, and we give it a vocab term, a feasible region. So we're going to go through, graph both of these systems, or not both of these systems, excuse me, both of these inequalities right here. I'm going to graph this one first, then this one. I'm going to see where, if any, there's overlap. And if there's some overlap, that's it. That's my feasible region, and that is my end game answer. So it may help, just depending on how your brain works. My brain tends to do this sometimes, right? I can rewrite this as x squared minus y equals 0, right? And this one, I can just swap out the inequality symbol and go 2x squared plus y equals 12. I think I'm just more used to graphing things with equal signs. So if I solve this for y, this is the parabola y equals x squared, one of my toolkit functions. And this one is a little different. This is going to be y equaling negative 2x squared plus 12. All right, so just thinking about this, this is our toolkit function, right? We know it's a parabola. This one here, it's got the plus 12, so it's been shifted up 12 units. I've got the negative, so it's been reflected over the x-axis, right? So now it's going to be a sad parabola. And it's got a compression factor of 2, right? So it's going to be a little bit skinnier because it's rising twice as fast. Or really, because it's upside down, it's decreasing twice as fast. Okay, so if I want to graph these, a good thing to do, if I can, is figure out where they might intersect. Because if I wanted just to do a quick and dirty graph in my head, right, there's my toolkit function. And then I've got something up at positive 12 for the y-intercept, and it comes down like this. Right, I can see that that's, if I sketch my happy parabola and sad parabola, I've got that. And I don't know, do I want to shade this region out here, this region on the side, this region down here, this one off to the side? I'm not sure. And what would help me is to figure out where are the actual intersection points. So if I change, and I did change all of these to equal signs, I'm going to go ahead and try and put this together, right? I'm going to go ahead and try and solve this as a system of equations first, and then I can move to the graph. And if you want to move right to the graph, you're more than welcome to. But if I look at this, if I think of x squared minus y equaling 0, and I think of 2x squared plus y equaling 12, it's set up for elimination. If I add these together, the y's do happen to cancel out. So I'm looking at 3x squared equaling 12. If I divide that 3 on both sides, I get x squared equaling 4, which is going to give me x equaling plus or minus 2. All right, and if then I want to determine what y is equal to, and I'm going to scooch this up just so we start to have enough room, I can plug x equaling 2 into either, actually I'll point to either of these two equations, and I can solve for y. But let me move this up just so we've got some more space to do all this, because we're definitely going to need to graph. All right, so let's try the case when, and can we see this over here? Yeah, x equals 2. All right, so if I want to try x equaling 2, I know x squared minus y is equal to 0. So 2 squared minus y equals 0. Or when I solve for that, right, I'm going to get y equals 4. So there's one of my ordered pairs. I know I'm coming in at 2, 4. All right, let's try it when x is negative 2. Oops, forgot my equal sign. So now I'm going to have negative 2 squared minus y equaling 0. I'm still going to get y equals 4. So my other ordered pair, my other point of intersection is negative 2, 4. And that's just going to help ground me when I go to graph these. And again, if you didn't need these intersection points, okay, I just like to have them. Okay, so I'm gonna go ahead and graph this. So let's go ahead and I make the sound effects if needed. All right, I'm gonna go ahead though, X, Y, count up to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, 12. All right, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So things I'll pay attention to. Okay, 2, 4 is going to be an intersection point, and then by symmetry, negative 2, 4, also going to be an intersection point. I know my original parabola y, x squared minus y goes through 0, 0. It's also going to go through 1, 1, and negative 1, 1. So here is that first parabola. And what I'm gonna do before I put this second one on, I wanna see based on this inequality here, right? And because it's less than or equal to, I'm gonna keep the solid line. I just wanna see, do I wanna shade above or below, right? And I'm gonna do this now because once I add the second parabola, it's gonna get that much more cluttered on here. So I just wanna see, do I shade up here or do I shade down here? Just keeping that in mind. Okay, so I can pick any test point that I want. All right, and if I want to pick a test point, I just don't want to pick one that's on the parabola. So let me try something like, well, 1, 1 is on the parabola. Let's try 0, 5 again. I think I chose 0, 5 last time, but 0, 5 is not on the parabola. It's up here. Let's see if 0, 5 is true. So if I go ahead and do this, right, if I have 0 squared, right, minus 5, is that less than or equal to 0, right? So I'm just going to say for right now, I'm going to do a test point of 0, 5. All right, let's see if that holds true. So if I do that, 0 squared is 0, 0 minus 5 is negative 5. So is it true? Is negative 5 less than or equal to 0? That is true. So I want to shade this. And I'm going to do it lightly right now, only because in a moment I'm going to have to add a second shading and see where the overlap is. Okay, so far, this first inequality, right, I want to shade above the parabola. Okay, let's go to this second one, negative 2x squared plus 12. So I know here the y-intercept is 0, 12. All right, and then I can test out some points. I mean, it's gonna head down and go through 2, 4 and negative 2, 4, right? So I can kind of plot those here. Let me just kind of like that. That wasn't the best drawing, but it also wasn't the worst. All right, and again, I want a solid line because this is less than or equal to. And when I look at this second parabola, I want to decide, do I want to shade above it or do I want to shade below it? Okay, and if I want to shade above it, that's fine, right? If I wanted to shade all of this above the parabola, that's great. You can see the overlap would be here. If I want to shade below the parabola, you can see the overlap between those two shadings would be kind of in that football looking region. I'm going to pick 0, 5 again because it's not on this upside down parabola either. So let's see, is 2 times 0 squared plus 5 less than or equal to 12? I'm going to put a question mark. All right, 0 squared is 0. 0 times 2 is 0. Is 0 plus 5 less than or equal to 12? Is 5 less than or equal to 12? It is. So I want to shade this parabola over this point. So I'm going to shade below. And you can maybe start to see when I shaded above this parabola but below this parabola, the overlap was here in that football looking region, right? So I'm going to darken that. That region gets a special vocab name. This right here is called the feasible region. And that is our solution. What this is saying is that I put my pencil anywhere here, like maybe this is the point, -1, +3. If I plug that into this inequality and this inequality, they would both be true. Versus if you try to point up here, right? I'm going to say something like 2, maybe 2 for how high it is, like 220, right? It would work in this first inequality, but not in this second one because it's in the inequality off of the happy parabola, but not the sad. Or I should say it's in the shaded part of the happy parabola, not the sad. right? If I picked a point down here, an ordered pair, and plugged it in, it would not work on this first parabola, but it would work on this second one because it's in the shading of the upside down parabola, but not the facing up parabola. If I pick a point out here, neither inequality will be true. So all the ordered pairs in here in our feasible region hold true for both inequalities. Okay, thanks so much. Bye.